Good morning, everyone. I hope all of you are doing fine. Today, we are going to learn another new thing, which we know as doping in semiconductors. So, this is very similar to doping, which you have heard mostly in the athletics, that this person lost medal or Olympic medal due to doping. Here, we are probably going to use it for our advantage, and that is what we mean by doping for our advantage. So now, what is doping and what is resulting in this doping is what we are going to see. So when we say doping in semiconductor, to understand it fully, we have to go to the atomic picture of the semiconductor. That what is a semiconductor? As of now, we have been using a very simple atom and bond model. That's for like silicon, which is a group 4 element. Group 4 means that every silicon is connected to other 4 silicon with this bond, right? So that is the your simple bond model. Otherwise, we know this is what we are drawing in 2D, but in 3D, it will look very complicated, right? So that is what this simple model can serve. Okay, so then this is the model, and we discussed all different things when we were applying the temperature, how atoms are vibrating, how electron hole pair is generated, all of this. Now we are going to see if the temperature, we don't want to apply any external temperature yet, but still we want to put in charge into this some net electrons, more electrons or more holes into this semiconductor. What do we do? So for example, as of now, what you see is the state that this is intrinsic meaning, which we have seen in the other video. So you are welcome to check out that video where we talked about the electron hole pair, what is intrinsic, and the charge in the semiconductor. So in this, intrinsic means that your electron density and your hole density are same. What does it mean? It means that the floor 1 and floor 0, if we have that picture with us, right? Floor 0 and your floor 1, which is your conduction band and your valence band. If there are holes here, which are created by because the electrons have gone, the number of or the density of these electron and holes are same, right? That is what intrinsic semiconductor meaning, right? And this is coming from these bond arrangement where you see every silicon is covalently bonded to other 4 silicon, and whenever there is a breakage of the bond, let's say between silicon and silicon, which could be due to temperature, because as we saw that at T equal to 0 Kelvin, which are absolute 0 Kelvin temperature, this quantity is tending to 0, right? So that is because there is no thermal energy in the system that this bond breakage will happen, right? So when we see that there's a thermal energy in the system, the bond will break, and the N, whatever N and P are generated, they will be equal, because one bond break in, that means the electrons is free and it has gone to the conduction band or floor 1, it has been updated to, and it is leaving a hole at the floor 0, right? That is what, or empty rooms at the floor 0. That is what the intrinsic mean. Now, what we want to do when we say doping, our goal is in doping is to make two combination, either N much greater than P or P much greater than N, right? What does it mean? Because we said that when N equal to P, yeah, there is nothing interesting because there are same number of electrons, same number of holes, right? And these electrons probably could go back after this recombination, which is happening. I want in my semiconductor, when there is, I can provide a net number of electrons or net electron density much be higher than the hole density, right? So that means now an external influence like temperature cannot do that job, because for that we need some kind of structural modification, right? Structural modification, that is what would be needed, right, if we want to achieve this. So this type is called, we know as this N doping or N type doping. and this type we know as the p-type doping, right? Okay, so n-type doping means there are more electrons in the semiconductor. P-type doping means there are more holes in the semiconductor. But this cannot be done just by temperature. So that means there is a structural modification one has to do. Now the question is, what structural modification will result in this doping? So let's see. So one thing we saw, that because these silicon which we had, right? Let's say they are covalent bonded. There are 4 valence electrons which they are having in the outer shell of their outer shell, right, of silicon. Then now these 4 are, that's how the covalent bond is made, right? This electron which comes from another silicon or other silicons, right, which is bonded to this, the 4 electrons of that silicon. So now the question is, if we break any bond, we know that the electron will be relatively free. It may be upgraded to floor 1, but it leaves the hole, right? That it leaves that state. So now my goal would be, if I want to create a doping, is to change this atom itself, right? Because if I change the atom, which either has more electrons or more holes, then what would be the state of that atom? That it would by itself give away that electron. So for example, let's say I find an atom which comes with 5 electrons, right, in the outer shell. So let's say this is atom X, right? There are 5 electrons. I know when it is putting in the crystal or in the structure, it has silicon, 4 silicon on the other side, which it can make bond with. That is good. But what happens to this electron? This electron, it is not part of the bonding process because only 4 silicon were there around it, right? So that means this electron will now feel like, oh, I'm free. That means, when free means that if it is not bonded, it is the part of floor 1 or the conduction band, right? So now in this semiconductor, if you see, if there is any bond breaking which is happening also, you will see that your n would be much larger than if you have number of atoms, x atoms, which are replacing, which we can also see how many atoms would we need if we want to achieve a certain doping. But that is a very prudent way or practical way to modify the structure using atom X or incorporating the atom X into this crystal structure or the structure of silicon or the semiconductor and have this. Wow, interesting. That is your N. And if I go, I find another atom, which is atom Y. And now this atom has one problem. This atom has 3 electrons rather than 4. So that means if I were creating a 4th electron, right, there is a hole with it which I would create, right? Which is what is the meaning of that? Obviously, these two will cancel each other, right? So it has 3 valence electrons. Valence electrons in the outer shell, right? That is the atom Y situation. Outer shell. Okay. So now the question would be, when I put this into the crystal which has the silicon, right? You see the, obviously the 3 ones are direct, right? The 3 atoms can make those bonds, right? With this, so this is one bond, this is one bond, this is one bond. What happens to the 4th one? Obviously, that was the electron was not existing, but we created a representation where electron hole pair, because they cancel each other, right? We created an electron and a hole in that. So now this electron, we can think that it is bonded, but what is left now is, you can see what is left is this hole, right? Which also feels it's free, or it is basically now, because holes can only stay in your floor 0. So when holes are free, they are in floor 0. That is what the condition of holes are. When electrons are free, they are in floor 1, right? That is what, how we see even the energy of the potential energy of the electron and holes are defined. Okay, just to tell you, the potential energy of the electron, because we know the potential energy would be Q into the potential, whatever potential you are applying, right? For electron, because Q is minus E, that is for electron. For hole, Q is plus E. So that is why potential energy will be also opposite to each other. And that is why you see that the hole, it is free in the floor 0, right? That is what the condition of this is. And what you see as a result of this hole, which is extra added, that your P can become much larger than N. So that is one of the way you saw. Now in a crystal, when I do the structural modification by incorporating, how you are doing structural modification, you are doing by incorporating what? Atom X and atom or atom Y, right? Depending on P or N type you need. Now this intentional, when we look at the periodic table, then we can figure out that which are the group 5 atoms. So these are called group 5 atoms. Group 5 means that they are coming from, that they are having 5 electrons in their outer valence shell, or 5 valence electron in their outer shell. While these are the atoms, these are the groups which atom Y comes from group 3, right? So that is typically you can see in your periodic table. Some examples of atom X are, atom Y, let's say, are boron, right? So when we see, you can see what are the other examples. Similarly, some of the examples of atom X are, one second, atom X are your phosphorus, arsenic, and other atoms, right? So that is the group 5 and group 4. So now you see, if you are putting some phosphorus while you are either growing the crystal or later, you can see that you will have this doping or N more than P, right? This is bound to happen if you are having these foreign atoms, as we discussed. So in this, you see that the foreign atoms actually are used, which are, it's a phosphorus or boron, are used for our advantage, right? Are used to make either N much larger than P, which is what we said as the N doping, or P much larger than N, right? So that is the intention of doing that, right? When we are doing the foreign atoms introduction. Okay. Now that is one, and we would discuss more on how does it affect this floor 1 and floor 0. This crystal structure, or let's say the structure of the hotel, is coming based on the design of the hotel. But if you incorporate some, you change the structure itself, right? There is a change which may happen in the how the floor 1 and floor 0 may look like, or there are different rooms or different, let's say, floor introduced in between. So the all of that we are going to look at in a separate video, where we look at what is the influence of doping on the this floor 1 or the band diagram, which we call it. As of now, our goal is to basically look at what is that happening in the semiconductor. First of all, how many atoms X or Y I have to put in if I have to put in a certain doping. And another question would be that how does it change the total charge density, right? Because if I have put more doping or more atom X, let's say if I touch the semiconductor, would I get current? Because there should be more electrons, right, in the semiconductor. So would that be the case, that I would be able to the current would be able to pass, or is it that the semiconductor would be still neutral? So all of these questions is what we are going to look at in next few minutes. So one is first the quantity. So typically, let's say if we are talking about silicon, right? So if we look at a particular silicon density, right? Silicon density. So density of atoms. So you can look at that how many atoms per centimeter cube. So per centimeter, how is the density of atoms decide? You decide because it's a 3D material. So you have a cube, let's say, and the cube dimension are, let's say, 1 centimeter by 1 centimeter by 1 centimeter, right? This is the cube dimension. And now you are seeing, okay, how many atoms can I fit into, or how many silicon atoms can I fit into this cube, right? So this is the same bond model which we are making. Very simply, you can think of this, that you are basically counting, okay, how many silicon atoms can I fit into this semiconductor. That is one way you can think of that you have um, basically you can see the density of atoms we can define, which would be that number of silicon atoms, right, in 1 cube of volume, 1 centimeter cube of volume, right? That is what our very direct way. This number could be in the range of 10 power 22, let's say, atoms per centimeter cube. We can exactly find out, you can find out online, but let's say it is in the range of, or the order of 10 power 22 atoms per centimeter cube, right? So because that would depend on your Avogadro number, and then you have to see in per volume how many moles you are having. So all of that you can figure out how many number of atoms I'm having in per cubic volume. Now the next thing would be, if I were to, let's say, let's create some desired doping. So for example, I want my n to be, let's say, for example, 10 power 18 per centimeter cube, right? I have to define again because it's a density, right? It's electron density. That means this many electrons per centimeter cube I will be having, right? This many electrons per centimeter cube is what I want, right? Depending on whatever my desired doping density. So you can see that how many foreign atoms, so how many atoms per centimeter cube. Obviously, these are, if one atom X is giving one electron, then it is basically equal to N, right? How many atoms X per centimeter cube? Because one atom X is giving one electron, right? Giving away one electron. So then, yeah, this is equal to N. But what we wanted to know in the whole crystal, because you replace this, how often it would be replaced, right? For that, you can easily take a ratio that, okay, so that means how many, rather than a cubic volume, we are asking how many atom X per silicon atom, right? So that for that, we can divide these two quantities. So let's say 10 power 18 divided by 10 power 22. So that means you have around 10 power 4, for example. So that means in 10,000 atoms of silicon, you will have one. That means in 10,000 atoms of silicon, one atom X will be found. Right? So that is how you can calculate that, okay, how many atom X I have to incorporate. And when you are doing, let's say, this doping intentionally, you need to know the dosage of your atom X which you are incorporating, right? So that is what you can find out, okay, how many atoms X I have to, or atom Y I have to put in. Now the other thing which I was talking about, the density, the charge density. So let's look at now again the semiconductor. We can look at the bond model, or it's easier to look at the semiconductor now. So what is happening, right? So let's see the bond model so that you can, yeah. Let's say atom X is introduced. So we are looking at only the N type, right? N silicon. So this is atom X, which is, let's say, phosphorus. 4 bonds are made with silicon, right? 1 electron is left in phosphorus, which is waiting for its rightful owner, right? So then if we see these 4 bonds which are made, 1 electron was there. Now let's say this phosphorus, because when it is put in, it is, we know when atom, if it is coming like this and it has 5 valence electron, in this state we say this atom is neutral, right? Neutral means that you are having, because it is having as many the electrons which is needed for it, the total charge of the atom, that means that is the neutral state of this atom, right? So if we take away any electron out of this atom, that means it's loosely connected and it is taken out of this atom, then you will see that this atom, so let's call this atom, because these are donor atoms, atom X, we call it, because they are giving donor, they are giving electrons. So donor is defined based on electron. So they are giving electron. So then we can call it the number of which we have already found at how many atoms. So that is what we call it the ND, right? ND means number or density of donor atoms. Okay. It is the same thing, how many atoms per centimeter cube. That is what basically we are defining. So why we are defining that, you will know. So let's say when this is the electron is very much part of the phosphorus, then this would be Nd, right? It's a neutral. But now if you take away an electron, what would be the charge on Nd which you will get? Obviously, if you take away an electron, then Nd will get Nd plus, which is what will give you Nd, right? That is the simple equation. So if you take this electron, is what is our donor electron, right? Which is giving us this N, right? And Nd plus is the donor atom, which we can say it's a ionized. Ionized means because there is a charge, that means it has given the electron. Ionized means it has given the electron away. Okay, so that is what would mean for this, that it would get Nd plus, and this whatever is coming from N, right? So as we saw that if there is no problem in the sense that all the atom X can give away this electron very nicely, then Nd plus would be, or Nd equal to N, right? Or N equal to Nd, right? Because they can give very nicely. But there could be cases where they cannot give very nicely, which we'll discuss in whenever we discuss the temperature dependence later. For now, the main goal for us is to understand the charge density, which we are talking about. So charge density, if you see, we talked about in the semiconductor, if there are similar instances, we have for acceptor, where atom Y, you see, atom Y is a acceptor atom. Acceptor means it's accepting the electron, right? Again, it is defined based on, though it is giving away the whole, but is accepting the electron. So the equation would be now, because it is giving away, accepting the electron. So that means you have Na, which is getting electron and becomes Na minus, right? So that is the case which you see in this case. Okay. So then now you will see that this would become Na minus, right? This one, which are the acceptor atoms which are ionized, right? That means they have received the electron or give away the hole. So this is the state. Now we see the different kind of charges. So let's say we started with some N, some P, which were either thermally generated or generated through doping. Then we also have Nd plus now and Na minus. Wow. There are 4 different charges which we have within the semiconductor. So if one needs to now put this all into one total charge density, you can say that I can put just multiply with the charge, that whatever the charge they have, N is having negative charge, so minus Qn, P is having positive Qp, Nd is positive, and this is negative. Done. So that is the total charge density in the semiconductor which I will have, right? And when I say that it is neutral, is the reason because Nd plus, we know, is equal to N. If all atom X have given away their electron, right? Similarly, Na minus would be P if all atom Y have given away their electrons. Sorry, given away their holes. And the N and P, whatever is generated even from thermal, N will be equal to P. So then we will see that that is the case. So then if we look away the row, if that is the case, then you will see that this thing will turn out to be 0, which is what we know as the that semiconductor is neutral, right? Or neutrality in the semiconductor, because you have the total charge. If your total charge density which you look at, you see that it is 0, right? That is what the meaning of the total charge density 0 meaning. And then we saw the implications of it in another video where we looked at, if we now based on this charge we are calculating electric field, what is happening in our semiconductor. If this charge is not it's finite, then what would happen? So all of this one can now look at. So with that, I will end here, and happy learning. Keep growing to all of you. Thank you.